you absolute legends. My name is Eric J. Choi, and I'll be going over explainer video 5.1 that goes over how sound canceling headphones work, kind of like the one I have right here. And jumping right into the problem. Noise canceling headphones are an application of destructive interference. Each side of the headphones uses a microphone that's built in to pick up noise, delay it slightly, and then rebroadcast the noise next to your ear, where it can interfere with the incoming sound wave of the noise. Suppose you are sitting 1.8 meters from an annoying 110 Hz buzzing sound, maybe like a faulty device that you have in your house. So what is the minimum headphone delay in milliseconds that will cancel out this noise? So as you can see from my beautiful diagram right here, I drew you a wonderful set of Bose headphones, which has a microphone built inside that will capture the sound wave from the sound source before playing a delayed version of the exact same sound wave into your ear, such that it will destructively interfere with the coming sound wave to result in no noise being produced. So here is the sound wave produced by the sound source, and here is the sound wave produced by the microphone. As you can see from my diagram right here, they're the exact same sound wave, but if that sound wave was brought here, you see how the top and bottom part are equal? And since they're equally destructively interfering with each other because they're the exact same sound wave, it'll ultimately end up as no sound being produced. Now we can finally start the problem. It was kind of a bait for them to tell you that it was 1.8 meters away because it's kind of useless to us in this problem. We know that the frequency is equal to 110 Hertz. So we can just use that to find the wavelength of the sound wave using the formula that we probably all seen before. Velocity of the wave is equal to lambda times f. So we plug in the speed of sound that we know from whatever source you like. So I chose a textbook, but you can find it from Google too. 343 meters per second divided by the frequency that we know is equal to 3.12 meters. And the exact path difference that we want it to be delayed is equal to 1/2 a wavelength, which means it's the same exact sound wave, but if we delay it by 1/2 of a wavelength, then it'll get into the arrangement. If they both overlap, they'll destructively interfere to result as this. So right here, the path difference is 1/2 of one wavelength. So that's just this value that we found up here divided by 2, which results as 1.56 meters. Therefore, to find the delay time that will cause that change in wavelength, all we have to do is plug in the actual distance that we want and divide it by the speed of sound, because in units it'll all cancel out to finally result as seconds. So t is equal to the distance that we want to delay it divided by the speed of sound is 1.56 meters divided by 343 meters per second. And that ultimately leaves us with 0.0045 seconds or 4.5 milliseconds. Thank you for listening, you absolute legends.